Swayam Prabha. Digital India. Educated India.
Hi everyone, welcome again to the course of structural biology. We are going through structural biology techniques. We have already discussed high resolution technique like crystallography in details, high resolution technique like NMR spectroscopy, and from NMR we have also introduced spectroscopy, but today it is a new module. We are continuing from the NMR spectroscopy to introduce other spectroscopy which are giving us low resolution structure. So, today it is the introductory class of the module spectroscopy. So, the science of spectroscopy grew out of studies of the interaction of electromagnetic energy with matter. So, it is the interaction, how the light rays come and interact. As you see this picture, this interaction could be reflection, transmission, absorption, scattering. With this different type of interactions with different electromagnetic spectra, there are number of spectroscopies. We will discuss about them. When light shines on an object, means light interact on an object, we know that part of the light is scattered and a part is absorbed. Of the initial part that is absorbed, some is later emitted as light of a different color or wavelength. Spectroscopy is that science which attempts to determine what specific energies and amounts of incident lights are absorbed by specific substance and what specific energies and amounts are later re-emitted. If I try to forget definitions, because definitions are always tough. If I want to give you an idea of what spectroscopy is, as I told, when light comes interact with matter, they have different type of fates. It is an attempt for us to follow those fates, to change the wavelength, energy and all of the rays, and through this interaction of light and matter, we want to see that if we could characterize some substances. That is what spectroscopy is used to do. Optical instrument called spectrometers reveal in photographic or printed records as a series of specific wavelengths or frequencies the light energies absorbed and emitted. That is where the study is happening. These records in turn referred to as spectra provide us with important information pertaining to the atomic and molecular structure of the substances on which the electromagnetic energy is focused. So, you have a series of substances, you have a solvent, group of solvent, you have an unknown substance. What we want is, we do this series of experiment, we find out if there is something called fingerprint. I will talk about that. These spectra provide us with fingerprints, as I was talking about, that are characteristic of, and therefore, it is an unique connection to the different element compound to those fingerprint. For example, I am not talking about, because I am talking in series with different spectroscopy and their characteristics. Do not go to any science, just imagine you have a molecule A and molecule B. If you put some ray on them and you get differentiated reaction, you could have recorded them and you could use that differentiation for recognition. That is what we are doing in spectroscopy. So, as I was talking about the term fingerprint, what is fingerprint? Let us discuss that. So, what we did, we considered three elements: hydrogen, helium and mercury. Now, if you want to differentiate between them, definitely we want that, right? That is how we could do our novel experiments. So, you have to take the help of a special instrument. With the help of the special instrument, you will get characteristic fingerprints which will guide you to differentiate between the three elements. So, this is hydrogen, helium, mercury. As I told, these are gone through a experimental process using a special instrument. When you see, to your surprise, you see that there are lines, and these lines are different for hydrogen, helium and mercury, the pattern of the line. You see, this is the pattern of the line for hydrogen, this is the pattern of the line for helium and this is the pattern of the line for mercury. The process of this characterization could be applied in many things and broadly everything. That is why we are spending so much time to understand the general principles, because if you understand what is the general principle of spectroscopy, then you go and you see that by changing energy, by changing different parameters, newer spectroscopies are developed and studied. Very interestingly, this gives rise to a complete field to study the characterization of different elements, atoms, atomic states, molecular interactions, etc. And this special instrumentation broadly called spectroscopy, which is our topic. Before going into the science, as you know from my trend of classes, we will take a look at the history of the spectroscopy, how it grown. In ancient time, Egyptians and Greeks thought about light and color and considered light to be mostly something that emanated from the eyes. The great minds of Ptolemy, Plato and Aristotle, they tried but failed to perceive a possible application that might involve light as we knew it now. Following the Middle Ages 400 to 1350 AD and the Renaissance period 1350 to 700 AD, ancient classical ways of thinking gave way to more creative academic analysis and crude optical instrument began to appear. So, if you stop here, just put your thinking what we want. We have a material, let us say A, we want light to come here and do different things, be it scattering, be it absorption, be it transmission, anything, and this anything will create a change. The change would be detected and that we call spectra. So, by spectra we mean a characteristic spot or line. So, you put an energy in a matter and record the changes, and by recording the changes you want to identify something. That is what spectroscopy is. So, in that time, in the Renaissance period, optical instruments began to appear, which are very crude form of modern spectroscopy. Scientists like Johann Kepler, Wilbur Snell and Galileo Galilei used combination of lenses in telescopes to see distant objects. Sir Isaac Newton in the latter half of the 17th century showed how a prism broke white light passing through it into a rainbow of separate and distinct color. That is an innovation which gives him the title, or we entitle him to be the father of spectroscopy. As you see here, white light is coming here and it is breaking to 7 different lights. All through these years, the best scientific mind puzzled over the question, what is light? The corpuscular or particle theory of light was championed by Sir Isaac Newton and seemed securely entrenched in the mid 1700s. Later, the work of Christian Huygens, Thomas Young and Augustine Fresnel lent considerable support to the wave theory of light. So, there was a classical theory, as we know, mainly contributed by Sir Isaac Newton, whereas wave theory of light is also coming. So, the battle between light as a particle and light as a wave continued on into the 20th century, with intellectual giants such as James Clerk Maxwell and Albert Einstein providing significant evidence for one or the other model. So, it takes really time for scientists to be coming to an agreement from other part of our discussions and all in physics, that the theory of light as a wave and particle duality. But unfortunately, in the midst of all the theoretical turbulence on the nature of light, the science of spectroscopy was nevertheless taking shape. It was slowed down. In 1802, a physicist named W. H. Wollaston used a prism, lenses and a narrow beam of light to produce an image of a single wavelength of the light. That is a landmark. So, if you see, this is the analysis of the experiment what Wollaston have done. Following this work, with the help of a different light dispersing element, a diffraction grating, scientists produce similar monoharmonic images of split light. The splitting of light is more coming into front and its applications. The spectroscope as an instrument became a practical laboratory instrument in the hands of German physicists such as Joseph Fraunhofer. I am sure you know about him, I am coming back. J.R. Kirchhoff and Robert Bunsen during the first half of the 1800s. As I told, Fraunhofer sounds very familiar because of the study of solar energy and the discovery of narrow dark lines in the solar spectrum, the Fraunhofer lines which we know. And with the ongoing analysis of light sources based on flames produced with Bunsen burners, there appeared bright lines as well as dark lines. There happens the launch of science of spectroscopy. Scientists understood then that the dark and the bright lines seen in absorption and emission were uniquely characteristic of the internal makeup of chemical elements. See, when you are working on a novel field of science, initially the dilemma is you do not know how to use it. That is why this understanding was very significant, because when people understand that the dark and the bright lines are characteristic of molecular structure. They understood that if we could start recording them, if we could have get instrumentation to study them, it would be fundamental, it would be very informative to know about the or to detection of the molecular structure of the small molecule to many things. That time scientists assume correctly that the energy in light could somehow excite the internal motion of atoms and molecules, extracting energy from the light at certain wavelengths, thereby giving rise to the narrow absorption lines. That is where a very correct direction takes place towards the modern spectroscopy. Similarly, heat or electrical energy could excite internal motion in matter, which would then radiate away the absorbed energy as light, accounting for the bright or emission lines in the spectra. In every instance, the energy that was directed onto the target substance to excite the internal motion of the electrons, atoms and molecules could be described as a well known part of the electromagnetic spectrum, which is something we have to study in detail to understand spectroscopy. So, electromagnetic wave and the spectrum. The electromagnetic spectrum is a range of all type of electromagnetic radiation. Radiation is energy that travels and spreads out as it goes. The visible light that comes from a light source and the radio waves that come from a radio station are two type of electromagnetic radiation. So, how many of them are there, what are their property, how their distribution, all are depicted in a electromagnetic spectrum. If you could understand electromagnetic spectrum, you understand a very critical part of spectroscopy. The other types of electromagnetic radiation that make up the electromagnetic spectrum are microwaves, infrared light, ultraviolet light, X-rays and gamma rays. Development of an electromagnetic wave. So, how you create a electromagnetic wave? All the electromagnetic waves are created by accelerating electric charge. Thus, the frequency, wavelength and energy of electromagnetic waves all depend on charge acceleration and just how this acceleration changes with time. For example, if you take some particular one, it would be helpful for you to make or get some numbers. Electromagnetic wave emitted by the accelerating charge is equal to the frequency f of the charge motion. If the charge oscillates back and forth with a frequency of 3 times per second, it will emit a wave with a frequency of 3 cycles per second, which could be called as 3 Hz. To create light waves in the visible part of the electromagnetic spectrum, a wavelength range of 0.4 micrometer to 0.7 micrometer have to be. Electric charge must accelerate at a rate high enough to generate waves of lengths around 0.5 into 10 to the power minus 6 meters. So, now we know that for any wave v, the velocity equal to f, the frequency, into lambda, the wavelength, where v is the wave speed in meter per second, f is the frequency in cycle per second or hertz as we have shown here, lambda is the wavelength in meter. So, now when we have all this information for light in free space, where we know the v equal to 3 into 10 to the power 8 meter per second, and for the mid visible region of the light around 0.5 into 10 to the power minus 6 meter, the frequency from previously mentioned equation we will get again f equal to v by lambda, which calculate out 6 into 10 to the power 14 Hz. So, you could understand this is an tremendously high value number. So, clearly there are no ordinary mechanical motion of charged substances at our disposal that can attain such high frequency. That is the challenge. Only in regions inside atoms and molecules where the electrons move very rapidly around the nucleus and where atoms vibrate and oscillate very rapidly in molecules can such high frequency of moving electric charges be realized. So, if you see, this is a system where the electric charge is accelerated and wave is produced with a frequency f and wavelength lambda. So, this figure demonstrates the creation of a single wave by an oscillating charge, and then how you use it for experiment. There is a set 3-stage formation. So, how this the single wave, how such charge made to oscillate along the arms of an antenna give rise to the electromagnetic waves moving outwardly in regions surrounding the antenna. So, you create a single wave and then from single wave how you make the electromagnetic wave. So, you see there is a AC power source, the opposite terminals of an AC power supply connected respectively to the upper and lower arms of the antenna generate electrons that accelerate up and down the two arms, if you see here. In the stage 1, this is the stage 1, the accelerating electrons are moving downward in both arms and create the outward moving electromagnetic field with the E field directed downward. As the applied AC voltage changes polarity, so does the direction of electron flow in the arm, and so then the outward moving electron fields change direction in the next stage. As the electron flow in the arms of the antenna continues to change the directions, the newly produced electric fields are created next to the antenna and the previous fields are forced further outward as in the stage 3, where finally they may be detected by a similar receiving antenna. There are series of that antenna. So, you see the number and how this big number is only possible to create inside atoms molecules. The single wave is generated here and then the actual electromagnetic wave which is going for experiment is created here. Coming to the electromagnetic spectrum, as I talked about, if you start from in terms of wavelength, it is started from gamma ray where the wavelength is very low to radio waves where the wavelength is very high. In between there are X-ray, ultraviolet, visible, infrared, microwave. So, this is what we call electromagnetic spectrum. So, from our previous knowledge, now we know the accelerating charges produce electromagnetic waves. There are many levels in the structure of matter where moving charges exist. Some of the more obvious are electrons in an atom, freely moving electrons in conducting metals, vibrating atoms in molecule and charged particle in a nucleus. Thus, there would be two factors which result in many different type of electromagnetic waves which we see in general experiments and all. One, the source of the charge motion, and second, the acceleration inherent in the motion. In many different type of electromagnetic waves are categorized according to their origin and their frequency or wavelength values. A typical organization of the electromagnetic is shown here. This is the one which we call electromagnetic spectrum. Here we are discussing the energies underlying these processes correspond to different regions in the electromagnetic spectrum. If we start from radio, we know that we have radio which capture waves emitted by the radio station. So, radio waves are also emitted by stars and gases in space, and as you see they are very high wavelength. So, the energy is low because as you know energy is inversely proportional to wavelength. So, the radio frequency region has very low energies that correspond to the energy differences in the nuclear and electron spin states. These frequencies therefore find application in nuclear magnetic resonance and electron paramagnetic resonance spectroscopy. Also you remember we have discussed this earlier, because this NMR and EPR they are operating at the high wavelength, which means low energy region. They are non-destructive, non-invasive method. So, you could plan instrumentation which could work directly on a living organism, as we have discussed about MRI using the nuclear magnetic resonance spectroscopy. Coming to microwave, microwave radiation will cook your popcorn in just a few minutes, but it is also used by astronomers to learn about structure of nearby galaxies. Microwave have energies between those of radio frequency, radio wave and the infrared, and find application in rotational spectroscopy and electron paramagnetic resonance spectroscopy. Coming to infrared, in infrared the energies associated with molecular vibration fall in the infrared region of electromagnetic spectrum. Infrared spectroscopy is therefore also known as vibrational spectroscopy, because it is working with the vibrational level of the atom, it operates there. Is a very useful technique for functional group identification in organic compounds. In addition to infrared, Raman spectroscopy also operate in that level, and that is why infrared and Raman are competitive. They are affecting a single molecule into different way. So, combining infrared spectroscopy and Raman spectroscopy would always be giving us more information, and in the later part of this module we will discuss about this in details. So, this is the infrared region. Visible one, our eyes detect visible light. Fireflies, light bulbs and stars all emit visible light. Whatever we could see is visible. These are involved in electronic transition in the molecule. So, these are all in the visible range from 400 to 780 nanometer wavelength. Ultraviolet radiation is emitted by the sun and a region skin tans and burns. Hot objects in space emit UV radiation as well. UV regions are involved in the electronic transition in the molecule. The spectroscopic method using UV or visible light, therefore, they are very well used in UV vis spectroscopy. X-ray, where we see the use of X-ray mainly, we go for bone fracture, we go for our dental problem. Dentists use X-ray to image our teeth, and airport security, if you see, they uses them to see through your bag. Hot gases in the universe also emit X-rays. X-rays are high energy electromagnetic radiation and causes transition in the internal electrons of the molecule, as we have discussed when we are going through X-ray crystallography. So, this is the range of X-ray 10 to the power minus 4 to 10 to the power minus 3 micrometer in wavelength. Gamma ray, doctors use gamma ray imaging to see inside your body. The biggest gamma ray generator is the universe. So, this is the gamma ray range. So, we are coming back, we have seen that spectra, and that was starting of our conceptualization of spectroscopy. We assume that looking at those spectra we could differentiate hydrogen, helium and mercury. But now if you see something more, very interestingly, this gives rise to a complete field of study we talked about of different elements, atoms, atomic states, molecular interactions, and is called spectroscopy. And we now know that the phenomenon is due to the interaction of matter with light. But now we have something additional to look at. If you see, we will look at that if you put wavelength and color, you will see that the bands are even more categorized. So, you get more characterization of those spectral lines. So, that would help you towards developing core concept of the spectra. These lines which we have are called spectra. The representation of the lines are called spectrograph. The optical component with a periodic structure that splits light into several beams traveling in different directions are called diffraction grating or monochromator or spectrometer. The complete system, including the light source, a means to collect the light that had interacted with the tested items, a spectrometer for measurement, overall the machine is called spectrophotometers. So, these are the basic terminologies: the spectra, the spectrograph, the diffraction grating, monochromator and spectrophotometer. So, looking at the molecular mechanism of interaction of electromagnetic radiation with matter. In order to interact with the electromagnetic radiation, the molecules must have some electric or magnetic effect that could be influenced by the respective components of the radiation. In NMR spectroscopy, as we now know in very detail, the nuclear spins have magnetic dipoles aligned with or against a huge magnetic field. If you remember the last module, you could easily remember that we have the nuclei have protons and neutrons, while proton have charge and spin, the neutron have only spin, and because of the presence of them, they are working as a tiny magnets each of them, and once there is be a external field, then they would react to them, they would respond to them, giving us characterization of that element. Rotation of a molecule having a net electric dipole moment such as water will cause changes in the direction of the dipole and therefore in the electrical properties. Vibration of molecules can result in changes in electric dipole that could interact with the electrical component of the electromagnetic radiation. Electronic transitions takes place from one orbital to another. owing to the differences in the geometry, size, spatial organization of the different orbitals, an electronic transition causes change in the dipole moment of the molecule, helping us to characterize a particular atom, material, polymer, substance and what not. So, what are the type of electromagnetic radiation interaction with matter? Absorption, where light is absorbed; emission, light is emitted or released; transmission, light is allowed to pass through; reflection, light is reflected or bounced away; diffraction shows wave nature; refraction shows particle nature; interference, light is disturbed; scattering, light is dispersed; polarization, light vibration is restricted to one direction. So, these are the interactions. Coming to spectrum, spectrum is a graph or plot of intensity of absorbed or emitted radiation by sample versus frequency of wavelength, frequency or wavelength. Types of spectra, three types of spectra we generally see: continuous spectra, spectra obtained when white light passed through the prism, this is a continuous spectra. Absorption spectra, spectra obtained by absorption of electromagnetic radiation of the atoms, ions or molecules of sample, UV, visible, anything, this is a absorption spectrum. Emission spectra, spectra obtained by emission of electromagnetic radiation to the atoms, ions or molecules of the sample. So, this is a emission spectra. So, these are the common type of spectra we have observed in our experiments. Coming to absorption and emission, when a photon come and interact, it change the electronic state of the atom or molecule and then emitted. So, absorption of radiation is the first step in any spectroscopic experiment. Absorption spectra are routinely recorded for the electronic, rotational and vibrational spectroscopy. It is therefore important to see how an absorption spectrum looks like. A transition between states takes place if the energy provided by the electromagnetic radiation equals the energy gap between the two states. The thing, so E equal to h nu equal to h c by lambda, the delta E, the change of energy, this is what in NMR, which we have discussed in detail, if you remember the resonance. This implies that the molecule precisely absorb, remember the precision or Larmor frequency in NMR, the radiation of wavelength lambda and ideally a sharp absorption line should appear at this wavelength. So, to view the spectra, you have to take two coordinates. See here, I have taken two coordinates. I put wavelength in the x coordinate, I put absorbance in the y coordinate. Then if you allow, you get a baseline, very solid without noise baseline, and in some portion of that you get a line of absorption for the characteristic of that atom or molecule. So, in theory we should get a straight line and absorption line, but in reality the absorption line could not be that sharp, and I have made the experimental one, and you see that there is a band rather than a line. So, you would not get a theory like straight line, rather you get a band, because there are different experimental consequences which we are going to discuss. Okay. So, this is in theory, this is what we get in practical. Why the absorption line giving broad peak? One, instrumental factor. The slits that allow the incident light to impinge on the sample and the emerging light to the detector have finite widths. Consider that the transition occurs at wavelength lambda t. When the wavelength is changed to lambda t plus delta lambda or lambda t minus delta lambda, the finite slit width allows the radiation of wavelength lambda t to pass through the slits. As a result, a finite absorbance is observed at those wavelengths. The absorption peaks are therefore symmetrical to the line at lambda equal to lambda t. So, that is why the broadening happened. Sample factor: molecules in a liquid or gaseous sample are in motion and keep colliding with each other. Collision influence the vibrational and rotational motions of the molecules, thereby causing broadening. Two atoms or molecules coming in close proximity will part up the electronic energies, at least those of the outermost electrons, resulting in broadening of the electronic spectra. Motion of molecule undergoing transition also causes shift in absorption frequency, and that is significant, and that is known as Doppler broadening. So, instrument factor and sample factor. Now, intrinsic broadening. Intrinsic or natural broadening arises from Heisenberg's uncertainty principle, which states that the shorter the lifetime of a state, the more uncertainty is its energy. Molecular transitions have finite lifetimes, as we know, therefore, their energy is not exact. If delta t is the lifetime of the molecule in an excited state, the uncertainty in the energy of the states is given by delta E into delta t greater than equal to h by 4 pi, delta into delta t greater than equal to h bar by 2, where h bar equal to h by 2 pi or Planck's constant. So, these are fundamental reasoning, but there are other reason behind these lines becoming broad peaks. Another two more features which are worth noticing are the fluctuation in the baseline and baseline itself, which is not horizontal. So, if you see the baseline is not straight, which it is supposed to, and it is not horizontal. The small fluctuations in the baseline are referred to as noise. Noise is the manifestation of the random weak signals generated by the instrument electronics. To identify the sample peaks clear of the noise, the intensity of the sample peaks has to be at least 3 to 4 times higher than the noise, the signal to noise ratio. A better signal to noise ratio is obtained by recording more than one spectra and averaging. The noise being random gets cancelled out. So, you do the scanning, what we say. Instrumental factors are responsible for the non-horizontal baseline observed here. The light sources used in the instrument emit radiations of different intensities at different wavelength, and usually the detector sensitivity is also wavelength dependent. A reasonable horizontal baseline for the samples can easily be obtained by subtracting the spectrum obtained from the solvent the sample it is dissolved in. So, you could get the solvent spectra and subtract it, that is the best method to correct this. Coming to quantitative measurement. So, as I told, it is called spectrophotometer, an instrument that measures the amount of light absorbed or the intensity of color at a given wavelength. The intensity of color can be given a numerical value by comparing the amount of light prior to passing it through the sample and after passing through the sample. These quantitative measurements of light absorbed are the transmittance and the absorbance, which we talked about. So, the instrument setup, we are talking about very simple instrument. The production and analysis of a spectrum usually require the following: a source of light or other electromagnetic radiation, a disperser or grating to separate the light into its component wavelengths, a detector to sense the presence of light after dispersion. The apparatus used to accept light, separate it into its component wavelength and detect the spectrum is called spectrometer or diffraction grating. So, how we measure? It is going by Lambert-Beer's law. So, Lambert-Beer's law, the light of a particular wavelength enters the sample, I0 is the initial intensity and its change which is I1, L is the path length and C is the concentration and alpha is the constant we will talking about. Light scatters from particles in solution, no momentum change, reducing light transmission. Light is absorbed by molecules, particles, momentum change and re-emitted at different wavelengths, reducing light transmissions. Lambert's law: when a ray of monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the length of the absorbing medium increases. Beer's law: when a monochromatic light passes through an absorbing medium, its intensity decreases exponentially as the concentration the absorbing medium increases. So, transmission and absorbance we talked about. Transmission T is given by the equation, it is equal to I by I0, the change intensity and the initial intensity, where I is the intensity of the light after it has gone through the sample and I0 is the initial light intensity. Absorbance is related to the percentage of T, A equal to minus log T equal to minus log I by I0. So, it comes here absorbing sample of concentration C and changing to I, this is the path length, it would be, it could call B, it could call L. So, as Beer-Lambert law, the linear relationship between absorbance and concentration of an absorbing species, absorbance equal to A or alpha L C, A or alpha into L into C. A is the absorbance, the capital A is molar absorptivity, as I told it could also call alpha, epsilon in liter per mole centimeter. L is the path length in centimeter, C is the concentration of the analyte in mole per liter. A, as I told, it is molar absorptivity. It is sometimes called extinction coefficient, a wavelength dependent constant for the species being analyzed is epsilon. L is the path length in centimeter, the diameter of the cuvette or sample holder, which is the distance the light travels through the absorbing sample, becomes a constant when the same cuvette is used for samples. C is the concentration. Generally, the main use of Beer's law is to determine the concentration of various solution. How? As we know, A equal to epsilon Cl. So, this could be fixed by fixing the cuvette. This is characteristic. So, by measuring absorbance, we could find the concentration. A working curve is produced by plotting absorbance versus the concentration. So, here you see absorbance versus concentration, it is a straight curve and from there you could get to know the required concentrations. From a working curve, one can determine the concentration of an unknown sample by knowing the absorption. This is what it greatly used. So, suppose this is a plot of an absorption data, you have plot of the blue dye, you have plot of the red dye. Now, you overlay the plot and now you could have the plot of absorption versus nanometer of red and blue dye mix. So, in that way you could have characterized them, you could have known the concentration, and that is where it is very commonly used, because you get any spectrophotometer and you could have calculate the absorbance. So, any unknown sample you are working on, you make the solution and you could get the concentration of the unknown sample. So, we have discussed about the general principle of spectroscopy and how spectroscopy would be used. We talked about the electromagnetic spectra. In the electromagnetic spectrum, there is gamma ray. Gamma ray is used for quantum transition at the nuclear level. X-ray absorption, emission, fluorescence and diffraction, they are affecting the inner electron. Vacuum, ultraviolet absorption using bonding electron, UV visible absorption, emission, fluorescence spectroscopy, again they are affecting bonding electron. Infrared absorption and Raman scattering, also they work on 0.78 to 300 millimeter. They are working on the rotation and vibration of molecules. Microwave absorption spectroscopy working on 0.75 to 3.75 millimeter rotation of molecules. Electron spin resonance spectroscopy around 3 centimeter wavelength range, spin of the electron in magnetic field. This is kind of similar as we think about in the case of NMR. So, nuclear spin resonance, this is the spin of nuclei in a magnetic field 0.6 to 10 meter. And so, as I told, these are the different parts. Gamma ray working on the nuclear level, and gradually the wavelength range is enhancing, energy is decreasing. So, it from the high energy to low energy and reversely in wavelength. In the next few classes, we would talk about different spectroscopies like UV visible absorption spectroscopy, circular dichroism spectroscopy, fluorescence, infrared, Raman. Also, I would add a new technique. I want to discuss about Raman microscopy and Raman crystallography. Thank you for listening. If you have any question, please keep writing us. Thank you.